Good afternoon, and first, my thanks for being invited to come and speak to you today. I do apologise that the presentation is not the one that was originally advertised, but I felt that at the time it's probably not the best thing to cover, all things considered. Having said that, though, it did give me an excuse to talk about one of my favourite subjects, which is latent finger marks. Now, you might wonder why I'm saying finger marks rather than fingerprints. Let's just clear something up straight away. In the research space that I work in, a finger mark is something that's incidentally left at a crime scene, whereas a fingerprint is something that might be taken from you when you visit a police station or visit the United States, for example, when you cross the border, and China as it happens, when you cross the border. So, before we actually start talking about latent finger marks, I need to introduce you to, say, forensic science fundamental principle, and that is the Locard's exchange principle. Sometimes this is incorrectly paraphrased as every contact leaves a trace. It's actually rather more complex than that, more nuanced. You have to take into account the intensity of the action that might take place. And essentially it's all about the idea that there is an exchange of information when a person, an object and a place interact. And where these things overlap, there is a possibility of an exchange of information, and that might be probative, that is, may help in a criminal investigation. Any of you who have cats, dogs, grandchildren with long hair, you will be aware that you come into contact with them, there will be exchange of information. From a forensic point of view, it's not just the transfer, that is, where does the trace come from, what we would refer to as a source type situation. It's more informative than that, potentially. We have to consider persistence, that is, how long a trace may actually hang around after it has been transferred. So that may provide information as to a timescale in which a transfer may have occurred. It is also a challenge that if you lose the trace, it's not persistent, that will obviously cause problems if you are looking at an investigation later on. Increasingly, there is an interest in what we refer to as the activity level. Not so much what it is or where it came from, but how did it get there? This in particular has been the situation with DNA. That is, in many of these investigations now where trace DNA may be involved, it's not a matter of whose DNA it is, it's how did it happen to be at the crime scene. And we'll see different aspects of this in my presentation. So let's consider finger mark impressions, the ridge patterns that are on our hands and our feet and on the palmar surfaces. It's been long known that they are highly characteristic and can be used to identify someone. And that's what their original use in, I suppose you could say, modern law enforcement was, to identify individuals brought to police stations through the collection of their prints. However, it didn't take long for it to be realized that they could also be transferred, either through a combination of the whatever was on the hands, blood, ink, whatever, or, as we will talk about shortly, the hidden residue, the latent finger mark. And just to make it clear that finger marks can also be looked at, and are increasingly being looked at, from the activity level, not just from the source level. Here is some research from a colleague of mine in the Netherlands. And they set up shop at a large music festival to look at various research projects in the activity level to do with finger marks. One in particular that was rather intriguing was that they had pillowcases. And the proposition they had was, well, depending on where you find the finger marks on the pillowcases, you can distinguish between someone just putting a pillowcase on a pillow or someone smothering somebody. And the way this worked, they had a dummy and they asked people to do exactly that, either put the pillowcase on a pillow or use the pillow to smother the dummy. The argument being, and they did this with ink on their hands to leave visible marks. The idea was, can we actually see a pattern that we can then distinguish between these two different activities? Because that may well be very, very significant in a case. To give an example of the value of finger marks from the point of view of a source and from an activity, I turn to the conviction of Ian Huntley, who was convicted for the murder of Holly Wells and Jessica Chapman in the small Cambridgeshire town of Soham in 2002. This is a very, very interesting case. There's all sorts of trace evidence involved in this case. However, finger marks played a particular key role. In a building on the school grounds that he was the, janitor for, they found a rubbish bin. And inside the rubbish bin were the tracksuits, underwear and shoes of the girls, partially burnt, and they were concealed under a bin liner, a black plastic bin liner. Huntley's finger marks were detected on that bin liner. But the significance was that they were able to use imaging to show that the finger marks were in a pattern that you would expect from someone putting the bin liner into the bin. That means that he must have seen the clothing under the bin bag when he put it in. Of course he did, he put it there. But this was very, very important in terms of establishing the activities that he did in the course of his crime. Now, there's all sorts of different finger marks that you might come across in forensic investigations. But by far the most common type is the latent finger mark. Now, sometimes this is referred to as the hidden finger mark or invisible finger marks, and sometimes they are. That being said, again, anybody who's got a large screen TV and access to small children will know that latent finger marks aren't that invisible. I have in the past, when doing outreach to primary schools, encouraged them to go to Myers and you can have a bit of fun. So this is the most common form of finger mark. It's made up of whatever is on the surface of the skin. That is skin secretions, which will make a significant component, and other things, contaminants. They're not readily visible to the naked eye, and I suppose what really sets them apart is that they need some form of treatment to make them visible enough for subsequent use or exploitation in a forensic investigation. Now, recovery of them relies very much on successful detection and visualization. I separate the two there. Detection is, oh yeah, that's a finger mark. Visualization is actually that part of where you can actually see all the fine detail. And that's one of the challenges of latent finger mark detection. We're not just after saying, oh, that's a finger mark. We want that detail. There's been a wide range of physical and chemical methods developed for this process, and they're essentially based on the idea of trying to exploit the differences between the finger mark and the surface, what we refer to as the substrate, that it's deposited on. And this is made very challenging by what colleagues in the UK working for the British Home Office, in what used to be called the Police Home Office, let me get this right, the Police Home Office Scientific Development Branch. They point out that there's this thing which is referred to as the triangle of interaction. The latent finger mark is dynamic. As soon as you deposit it, it will start changing. Not only because of its inherent finger mark composition, everybody's finger mark chemically is going to be different. The environment surrounding that finger mark is going to have an impact, and the surface itself will have an impact. And so this makes this quite challenging. In terms of finger mark composition, broadly, it's been well established that it's essentially made up of three broad groupings. There's the eccrine secretions, which are water-soluble, essentially sweat. This is primarily made of water with some dissolved chemical compounds. In particular here, amino acids will be very important. Then there are the sebaceous secretions. These are the oilier, non-water soluble components. They come from glands, predominantly from wherever there is hair on your body. They are the skin's natural conditioner, as it were. And finally, there are contaminants, although contaminants is probably not the right term to use, because some of these things are things that you would deliberately put on yourself. So things like cosmetics, sunscreen. It's also, if you've been handling certain substances like drugs and explosives residues, they can also be detected in your finger mark. And indeed, colleagues in the United Kingdom have been working on that in the last 10 years. So that's the basic chemistry of the finger mark. What about the surface? Well, if you have a non-porous surface, glass, metal, plastic, varnished wood, you can think of the finger mark as essentially sitting on top. And over time, it will degrade, it will dry out, any water will evaporate, and the oils and so on will become more waxy. It's also very fragile, very easily wiped off. The primary way of detecting has been, for many, many years, it has been dusting or powdering. And that was, over 100 years now, that's been used. Around about half of the finger mark identifications per year in any jurisdiction, as far as I can tell, come from powdering for marks or dusting for marks. What happens, though, if you've got a paper surface? Porous surfaces like paper and untreated wood and textiles, they're rough. And paper is often found at crime scenes and in situations involved with crime. It's something that you really want to be able to collect finger marks from. But it's got a rough surface. If you try to powder, you'll just get a smudge. And this is where chemistry can come in, and this is actually how I got my first, research going in this space around about 20 years ago, was the idea that when you touch a piece of paper, the water-soluble component will absorb into the paper. The amino acids, in particular, which are present, as far as we can tell, in just about everybody's finger marks, stick to the paper. As long as the paper's kept dry, it doesn't migrate any further, it essentially has your finger mark there, invisible. You need to develop it with a chemistry. And for many years, people have used the chemistry called ninhydrin, which produces very nice purple marks. These days, we tend to try and use finger mark treatments that not only do they give you a color, but they also luminesce. That is, you shine a light on them and you will see light coming back. It gives it more sensitive. Anybody who enjoys a gin and tonic would have seen this phenomenon when they sit in the garden, that sort of nice little sort of blue glow. That's actually the quinine in the tonic water fluorescing in the ultraviolet light. So you're doing science when you're doing that. Well, that's what I tell myself anyway. So these finger marks here are actually developed using the treatment that's used here by the Western Australian Police based on a compound called 1,2-indane-dione, which is actually very similar to ninhydrin. It's probably the single best treatment for finger marks on dry paper and is used Australia-wide. You need a forensic light source to make it work because you're actually shining a sort of blue-green light, and then you view it through orange goggles and you see these lovely finger marks. Now, it's very effective. And one of the questions that I used to be asked early on in my career in finger marks was, well, how long does it last on a finger mark? How long does it last on paper? And I didn't know the answer. I do now. Best part of 90 years. All right, we were very lucky that my colleague, Dr. Stephen Blay in the UK, had in his possession documents from his grandfather that had been kept without anybody touching them for the best part of 90 years. So he knew that his grandfather was the last person to touch them, and he was able to detect finger marks on them. In a similar fashion, thanks to a colleague who was just retired from the Curtin Library, she had access to some notebooks. They were autograph books from the Netherlands. I gather it's a hobby for people to have these autograph books, which family members have signed. These were from the 1940s. In fact, one of our successful ones, I'm not sure that, I think that might actually be it, was a finger mark developed on a document about the day the Germans entered Paris in 1940. She also had a big bundle of letters from when she had a pen friend in Japan in the 1980s. And we were able to detect loads of finger marks there. As you can see there, letters 35 to 40 years old, there is something like 70% of the marks that we developed were potentially identifiable. Now, while 90 years is a long time, it's not necessarily forensically significant. 35 to 40 years is. That's very much within the boundaries of what would be considered a cold case. So, why are we doing research still? Because we know we don't detect every finger mark. We know that many go undetected. There's also potential new approaches to provide alternative methods or improve current procedures. And there are also challenges with modern surfaces. The rise in recyclables and compostables has made things a little bit challenging. Polymer banknotes. Now, for all of these, you want to have safe, simple, and inexpensive methods. These are things that are going to be widely used, probably by people without a major scientific background. Now, that was my entry into fingerprint research, in that around about 2003 or 4, I think it was, just shortly after I got into forensic research, a paper was published on the use of a natural product to detect finger marks. It's this compound here, genopin. Now, genopin is extracted from the fruit of certain species of gardenia. And it's been used for a long time by the native tribes in South America as a reactive skin dye. It stains the skin blue. And it's been known that's because it's reacting with proteins. This gentleman here, Professor Joseph Almog at the Hebrew University in Jerusalem, working with some scientists in Korea, established that it could potentially be a pathway to an alternative to ninhydrin. one of the reasons they were interested in it was that, I know it sounds an obvious thing, rather than giving a pink mark, it gives a blue mark. That might be significant depending on the background that you're looking at, right? It's as easy as that. But it was also luminescent. And Joseph Almog is known for his research in this space. He was one of the first to develop Fingermark treatments that luminesced. And in a rush of blood to the head as a junior academic, I emailed Professor Almog saying, do you know where we could get this Genopit? And his response was, call me Yossi. I'll put it in the post to you. 2003 is not a good time to be receiving a white powder in the mail from Israel. I did actually get a call from the AQUIS saying, were you expecting something from Israel? I said, yes, actually we were. And it worked. And my honours student at the time, my very first honours student in the space of fingerprint research, got some lovely results, as you can see here. But that set us thinking, is there any other sort of natural product that might work in the same way? And while looking through a magazine, my colleague, Associate Professor Kieran Lim, this was when I was at Deakin University, came to my office and he said, hey, look at this. Lawsone. It's thought to be the component that causes staining by henna. And to us as chemists, we looked at it, it had chemical features that made it look awfully similar to Genopin. And so this was just at the point I moved to Perth. I had one honours student who came with me from Victoria, Renee Jelly. She did her whole PhD on the use of natural products for Fingermark treatments. And this was my first ever paper in Fingermark detection. And it worked. And the idea was, well, it's a natural product. It's the potential it might be a bit safer, provides an alternative. And it set me down the pathway of Fingermark research from that point. Renee, or Dr. Renee Jelly, now works for the Western Australian Police as a senior crime scene examiner. Moving to more recent times, we've been increasingly interested in the use of nanotechnology for everything. So it comes as no surprise that also there's been interest in it for fingerprints. Why? Well, first off, if you've got a latent finger mark, you've got these ridges that you're trying to detect, visualize. If you have more particles that you can fit on a ridge, the better the better the resolution, you would think, in principle. You also would get, because of the physics of the situation, a higher surface interaction. So possibly you'd get more particles and they would stick better to the finger mark. With nanoparticles, we can do all sorts of things to the outside of them to either make them stick better or target particular chemical groups, which might improve selectivity. That is, it only detects the finger mark and not anything else. And finally, depending on what nanoparticle you're looking at, they can have rather interesting optical properties that you can modify. For example, they can be made luminescent. So I was very lucky to actually have a PhD student she graduated last year, Dr. Soru Shabhazi, who came to me as she actually was an expert in making nanoparticles as part of her master's in chemical engineering from UNSW. And she looked at two different aspects. And I've called it nanostructured materials because the Egyptian blue wasn't so much nanoparticles as nano dimensioned in one dimension. That is, they were a couple of nanometers thick, the particles that she made, but about 200 or 300 nanometers in length. And also quantum dots. Now, Egyptian blue is the world's most ancient known synthetic pigment. Not too surprisingly, it was discovered and invented by the ancient Egyptians. But then its secret to how to make it was lost for well over 2,000 years, until discovered late in the 19th century. And it's an intensely blue material, and it luminesces, but not in the visible like your gin and tonic, in the near infrared, which is not visible to our eye, but every single digital camera is a near infrared detector. All you need to do is take out a certain filter. It's a lot easier to be able to visualize than you used to be able to do. And why we're interested in it is there's not very much that is naturally near infrared luminescent, so hopefully you'll get improved signal to noise. You'll get a better signal and you'll see your image against a dark background. Problem is, artists' Egyptian blue is quite chunky and doesn't stick to the finger mark. But it has some interesting nanoscience behind it. If you boil it up in water, and I mean just boil it up in water, for a few weeks, that didn't sound so good when I said that, did it? But when you boil it up in water for a couple of weeks, it actually delaminates or exfoliates into these nanosheets, which Soru hypothesized would stick really well on the finger mark, particularly if we covered them with something that made it more attracted to the oily components in the finger mark. And it worked. So here we have what we refer to in our work as challenge substrates, deliberately patterned, difficult to see. And you'll see there's some polymer notes. We actually cut them up. You have to have permission from the Reserve Bank to do that. There are only 2 people in the Reserve Bank who can let you do that. One of them happens to be a friend. He's an analytical chemist like me who actually works for the the extensive research lab that they have. I called him up to find out where we would get permission. I said, "Where do we get permission?" He said, "Oh, you just ask me." One day we will send them back and they will send clean ones to us. I assume you'd call that laundering, but there we go. And it works. Now, these are all not, this is all photographs taken in the near infrared. And you probably can't quite see it, but if you zoom in close enough on some of those, you can actually see the pore detail. And because of the fine particles, they stick really well. We've just had a paper accepted that Soru finished as her last part of her PhD, that you can actually cut down the exfoliation time by doing it in methanol, and it's a lot easier to get rid of the methanol. You just allow it to evaporate, so there's your powder. We also worked, though, on true nanoparticles. And there's been a lot of work in this space, but one of the problems is that actual nanoparticles are not something that police will use because they're dangerous. Dry nanoparticles will go straight through a face mask. They're not interested in that. And there is another way, though, to apply nanoparticles to a finger mark, and that is to use a water-dispersed nanoparticle. To all intents and purposes, it looks like a solution. There used to be an old name for nanoparticles in solution. It used to be all called colloids and colloid science, which some of you would be familiar with. I'm not entirely certain when it got rebranded nanoscience, but that's the way in science these days. In fact, nanoparticle methods had been used for decades in fingerprint detection. A method called physical developer that's based upon the chemistry used to develop old wet camera film. And most of the police officers don't like it very much because it's really, really finicky. However, we were looking at hopefully using different nanoparticles. And one of the nanoparticles that shows a lot of, or class of nanoparticles that shows a lot of promise is something called quantum dots. They're rather unusual in that they exhibit different forms of luminescence, that is, colors of luminescence, depending on their size. And there's a lot of interest in these sorts of quantum dots for all sorts of things, like next generation screens for TV and phones, and also in the area of energy as well in terms of solar cells. And I was lucky enough to have an expert in how to make these working at Curtin, now Associate Professor Gohar Jia. And we sat down in my office and I said, this is what we want. And we went through a list of all the different things that we would like to have. Top of the list was we don't want them to be toxic. And he listened to us and he suggested, and he came up with a form of quantum dot based on copper, indium, and zinc. And here again are our challenge surfaces. And here again, it's not quite in the infrared. This is actually in the red end of the spectrum. And again, it worked. All of those treatments there with nanoparticles and so on were treating non-porous surfaces. Okay? We've also done work on porous surfaces. What people are interested in, though, is do you have treatments that can deal with both types? And this is an example here, gold nanoparticles, developed by a colleague in Switzerland, and we've been playing around with it for a few years now. And the advantage of this as a treatment is you can look at different things. Wetted paper. Paper that's got wet, you can't use an amino acid treatment on it because all the amino acids have been washed away. But you can use this gold nanoparticle method. Plastic surfaces like Ziploc bags. The police have an interest in this because, of course, Ziploc bags are what drug samples are put in by drug dealers. And so they would be interested in a method that would successfully detect fingerprints on there. And indeed, we had a police officer who worked on that. You might note there that we've been able to detect a fingerprint on the inside of a nitrile glove. It just occurred to me it might be kind of cool to see if we could do that. And we also, you probably just see it, we had a look at a compostable paper bag, a plastic bag. And we do actually see some ridge detail there. But all of that research has been deliberately depositing finger marks, what we would call deliberate finger marks. Does that represent reality? Well, no. What we really want to do is say, well, what happens if you do something? What finger marks can we detect? Where are they? And this is the space which we refer to as pseudo-operational trials. This is a very small, our first sort of attempt at this in a very small way. Aaron Horrocks there, who did his honours degree last year with me, he was looking at 3 different ways of detecting fingerprints on the sticky side of tape. One of them was based upon the Egyptian blue, the other was on quantum dots, and the third was a method that's used operationally, essentially called sticky side powder, which is essentially black fingerprint powder in a detergent mixture. And we're looking at this, we were thinking about what were the things that you might find tape on, and one of those is improvised explosive devices. And Aaron had to think very carefully about how he did this experiment. So he got transparent bottles with obvious, didn't put phones on them, we put something that was the shape of a phone, and then we had colleagues make them with tape. They had to be transparent bottles so that when they were stored in the lab, he had a big sign saying non-hazardous. We felt that if we had done something a little bit like the one on the far side there, we might have caused alarm and despondency, and I might have got what my father refers to, a meeting without coffee with the dean. You'll also notice there that we're using multiple donors because that has to take into account the chemistry of different people. And what we found was the Egyptian blue method, which was, I thought, oh, this is going to work. No, it didn't, which is always happens to me. The supervisor is always wrong. The quantum dots actually gave us some really nice results, and as did the operational method. And now we're now moving on to carry on this work to see if we can properly evaluate the quantum dots against carbon black. suspension as a method for use on sticky tape. But something that has arisen from all of our research over the years has been that the chemistry of the finger mark is really, really important. And so in the last 15 years, there's been an ongoing research in my group trying to understand the chemical and physical properties of latent finger marks using a wide range of sophisticated instrumentation. The two PhD students, Dr. Boudica Dora-Kambura, who worked on the physical aspects, while Rhiannon Bosley there has just submitted her thesis. She worked on the use of spectroscopy. We looked at the physical properties using a technique called atomic force microscopy, which is a complicated way of saying we were looking at how sticky the finger marks were on the nanoscale. Think of it as a little bit like the old needle on a old record player. And it could travel over the bumps of a finger mark, the individual droplets, and tell us something about the topography, but also how sticky they were. And what we can see here is that there's differences between the different droplets, which tells us, and it's not just differences broadly, one droplet is different from another, there are differences in adhesion within a droplet. If you look in particular at the natural one, you can see there are areas that are more strongly adhesive than others. What that tells us is that those finger marks may well have heterogeneity at the nanoscale, which could have an impact on their detectability. The problem is of looking at finger marks though, and the other issue that we have was we want to look at the chemistry of these finger marks in situ, so that we could, for example, maybe look at how they might change with age. That's very difficult. We're looking at tiny amounts of material. So it was actually suggested to me early on that one of the facilities we should think about was the Australian synchrotron. Now, Australian synchrotron is in Melbourne. It's just outside Monash University. It's, for all intents and purposes, what we're going to say here, it's a very, very powerful light source. It's actually a source of electromagnetic radiation, but for marketing reasons, they don't like using radiation in the title, so they say light source. But it's got light of differing wavelengths. We were particularly interested in it to start off with, that it provided very, very powerful light in the infrared. Light that could be focused down onto a micron scale to allow us to actually look at the chemistry of the finger marks in situ. And it's essentially about the size of a football pitch. Inside it is, for want of a better word, nerd heaven. Right, it really is. You bid for beam time, and then you get some, when you're awarded beam time, you go there for, say, 36 hours, and you work shift in, shift out, gathering as much data as you can. My colleague Georgina Sozia we're working on a project at the moment looking at cosmetics in finger marks. Rhiannon is currently at the synchrotron at the moment. I'm assuming, oh hang on, it's Sunday, so Sunday's a day off. But Monday morning, they'll be back to it collecting data. And that's a picture of me just to prove I get in the lab occasionally. Our very early studies would have been, around about 2010, thereabouts. And this is one bit of result from there. This is from a single droplet, no more than a few microns across, or two droplets. And they were finger marks collected from a 7-year-old subject, as he was at the time, just after a birthday party. And we collected them on a gold plate. 1 hour after the activity, which involved an awful lot of eating food of dubious nutritional value. And then 1 hour after his bath. And what you can see there is a dramatic difference between that chemical signal. And I'm not much of an infrared spectroscopist, but the ones who are, the folk who were at the synchrotron told me, that that has all the signs of things like hydrogenated oils and so on. Oh, it's a chicken nugget spectrum. Which I didn't realize at the time because it wasn't such a big phrase being used then. But what we're doing is we're actually exploring the activity level here. And this gives some indication that when you develop a new Fingermark treatment, you shouldn't focus just on the fact that you're looking for human skin secretions. There may well be other things present. This research that synchrotron then developed so that when Rhiannon came along, she actually did, her whole PhD has been about this. The idea is that we're not just looking at an individual finger mark, we can actually map them. So these are chemical images, these are false color images, and the blue parts are showing you the water-soluble components. The red parts are the non-water-soluble components. So essentially the eccrine and sebaceous secretions. And you can see there that across the finger mark, it's heterogeneous. But then if you looked at the individual droplets, you can see there's red and blue there in the single droplet. They're heterogeneous as well, which links in with the evidence we found from the atomic force microscopy. And indeed, when I first got into latent finger mark research, I was at a conference and I referred to finger mark secretions as being an emulsion. And a long time research in the space said, how do you know that? And I realized that nobody had actually shown it. This evidence was the first evidence to demonstrate absolutely that finger mark residue is an emulsion. But Rhiannon went beyond that in that she also started looking at the changes in the finger mark. And now again, I want to point out that little sort of video there, that is a finger mark drying over the space of 12 hours. Right? There's another video that goes with it showing the lipids that are present there being redistributed. So, yeah, I know it may sound, you may not think that watching water dry is terribly important, but it is. We found that these finger marks are drying out within 12 hours. So the fingerprint powders that are being used are probably adhering to the more oily components rather than to the water, because fingerprint people are not going to get to a fingerprint within 12 hours of it being deposited. It's going to be later than that. She also looked at, no one had ever looked at, what about the distribution of metals in a finger mark? And this rather terrific image of it, that's actually an image of a finger mark, and the different colors are different elements present. Again, we used a different form of light at the synchrotron. We used X-ray. This is X-ray fluorescence microscopy. When you hit compounds or hit materials with a certain wavelength of X-rays, it will excite the elements and you'll get X-rays emitted that will be characteristic of particular elements. And very, very sensitive. And again, we can look at things at the near micron scale. And we did a range of different finger marks, and one of them was spectacular because it had titanium in it, which is this one here. You think, well, titanium, where's that coming from? Makeup. And we also found when that person washed their hands and then gave another finger mark, it was still lots of titanium. And her response to that was, well, it should be. It's good quality makeup. But again, that ties into the idea of persistence. And we started to look at what happens if you handle objects of forensic interest, like a firearm barrel, or cartridge cases, or explosive mixtures. And we're able to show, yes, you do transfer that in your fingerprints. And we also showed that you only needed, say, 30 seconds of touching something for it to be there. We also showed that if you wash your hands, it's gone, so it doesn't last for very long. So, for example, if you found finger marks with traces of an explosive mixture in them, then you would probably be able to say, well, that was recent handling of those explosive mixtures. So what we've done over the last 5 years in particular, we've demonstrated the capability of the synchrotron to map all sorts of different things across a finger mark. And we're now increasingly beginning to look at how we can consider the activity level, hence why we have a group there at the moment looking at makeup in finger marks. But to finally wrap up my presentation, I actually, in a way, am returning to where I started in finger mark research. When I first got into finger mark research, one of the things that really interested me was the idea of, can we do things with safer, cheaper reagents? And it's taken me a little while, but I've begun to, I had this sort of term that I came up with a year or so ago called frugal forensics. The idea being that we can do forensics in a different way. And you might ask, well, why would we do that? Well, it's all about managing costs in relation to performance. You may be in an environment where you don't have access to top flight equipment. So what can you do instead? It may not have the same quality as what's available at the top end, but it gives you something, an ability that you don't have. One aspect that I was talking about before COVID hit, which I'm rather proud of, was what about interruptions to supply chains? Everybody knows about supply chains now. It was not such a big thing 4 years ago. When I was mentioning it, people said, no, there's no problem, you'll just get it sent to you. Not so straightforward now. We have to take into account that whatever we develop has got to be safe and to be used with minimal training. I don't mean minimal forensic training, I mean minimal chemistry training. The ability to do things without excessive amounts of personal protective equipment. And we have to take into account the possibilities of remote or austere short-term situations. So, for example, in a disaster victim identification situation. So just to give some example, this is Jem Fuhr, who worked for me in her third-year project. This is, I suppose, frugal forensics, or could you call it kitchen forensics. Those fingerprints, which they're not great, on the top there, on glass slides, they've been developed with turmeric powder, which is luminescent. And this was actually very old turmeric powder. It's been sat at the back of our spice cupboard for years. We're just beginning to explore the possibilities of it, because that's readily available. People have looked at it and to extract the stain from it to use with superglue fuming, which is a method I haven't talked about today. But I thought, could we just use the powder? Anybody know what that green stuff is? Anybody who's a bit of a health fiend here? No, it's not kale. It's spirulina, which, yeah, that's... Soru, my student, would agree with you entirely at the time. But we tried spirulina, but obviously it was an old batch. Jem went to a health food store and bought fresh, and it worked. It's a little bit difficult to see, but it's developed finger marks on those banknotes. It's near-infrared luminescent. So those are both relatively inexpensive. I know, because spirulina is actually marketed by a company for fingerprint detection, and I can tell you right now, it's a lot more expensive than buying it from your local health food store. When my group have laughed when they say frugal forensics, you mean that Simon won't pay for it. But this has actually gone further than that, the idea of using inexpensive light sources. Our main forensic light source is the Polylight, which is an Australian invention, by the way. It's $25,000. You can buy LEDs that are designed for amateur dramatics, and someone's pointing at the back saying that the light shining at me is probably one. $25 off eBay. And we actually tested it, and granted, it's not as good as a Polylight, but it'll still work at a pinch. And you might think, well, so what? Surely police people will have access to more expensive lights than that. I happen to know that in North America, in the United States, hardly any fingerprint people use indaned iron like we do here in Australia. They're still stuck with an anhydrous. And this has led to my two students in particular, where we're now looking at this in a more systematic fashion. And overall, this is all about latent fingermark development in what is referred to as the global south. So, and the objectives, the overall objectives, are to improve latent fingermark detection capabilities and facilitate their use in labs in jurisdictions with limited resources and challenging climates. So Jemmy Bouzin, who's my current PhD student, he's also head of the forensic unit for the Seychelles Police. And of course they have significant challenges being at the end of a very long supply chain and a very, very widely distributed but relatively small in terms of landmass jurisdiction. The jurisdiction itself, in terms of people, numbers of actual residents there who live there permanently, is probably no bigger than Willerton. So it is very small. My recently arrived, by recent, a week ago, it's taken her that long to get here, is Thais Lopez, who has come to me from Brazil. Brazil is a very large country. It's about the same size, I think, as Australia. They have a federal system. They have first-class fingermark treatment processes at the federal level in 1 or 2 labs. But out in the regions, very different picture. And her PhD will be all about trying to provide those fingerprint staff in Brazil with options that will provide better detectability of finger marks in a challenging environment. She arrived at the beginning of last week and I said, "Whoa, it's humid." And she says, "This isn't humid." Just to finish, this is not just forensics. My research group is now beginning to look at things to do with finger marks, to do with cultural heritage. So, for example, Karen van der Paal, who's just finished a PhD, she's writing up at the moment, looking at handling of paper-based objects in terms of the effects that finger marks will have. There's been a long story that in handling of objects, the arguments about whether you should wear gloves or not. And in fact, there was a paper where they stated, you don't need to wear gloves. Finger marks are 99% water. No, they're not. We know, because we did the research recently, they're around about 50% to 60% water. But that's only when you deposit them. Right? So, and there's detectable other stuff there. We know that's our living. Now, whether that'll have an effect on the object in a long term is another matter. But we see it, her work was about, well, providing archivists and people who work in that space with an understanding of what might be deposited on the paper. Alex Moore there is working on an MPhil in collaboration with the Corrosion Centre, where finger marks might leave damage on metal objects, which is her interest. She works in the museum sector. She is, shall we say, somewhat flabbergasted by the choice of the metal coverage of the staircase in the museum. I've not been to see it, but it's a spectacular example of what latent finger marks can do on a metal surface. What's really good is they're at 2 levels. You've got the adult level and the small child level, if anyone's seen it. All of the work that I've talked about today has been carried out over the last 15 to 20 years with a large group of people from around the world, from universities. In particular, I name them my former students and colleagues at Curtin University, other universities around the world, and law enforcement as well. And obviously, I'd like to thank the funding support from the university and from the Australian synchrotron. And of course, I'd like to thank this fabulous group of people. This is my research group, as it was just before Christmas. I need to thank Dr. Amanda Frick, my former student, for that wonderful quote there that we actually managed to include with a book chapter. She's a bit of a Terry Pratchett fan. We don't do just fingerprint research, but everybody who goes through the group does some fingerprint research at some point. And thank you for your attention.